Swayam Prabha. Digital India. Educated India.
So today we are going to talk about some of the examples of CT spectroscopy as it can help us. So the first example, we'll take that of polylysine. So over there, let me first find out what is the structure of this polylysine. Okay, so this is the structure of polylysine, which is actually nothing but a continuous sequence of lysine altogether. So like hundreds of lysine next to each other. So if you try to draw the primary sequence of it, so you will see it is lysine, 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 all these things. And then people try to find out what is the effect of this lysine on its different conditions of pH and temperature. And for that, what they did, they tried to figure it out how it looks like in the different temperatures. And that is the data they got. So you can see, so there are some difference. So this is just a simple absorbance rate. This is the absorbance data for this polylysine drawn over here. And what you can see that the bands, although changed a bit, but it is not showing a huge difference over there. And that is a little bit tricky to understand what is actually happening just by absorbance data. And let me tell you what are the differences. So over there, as it is shown that we already written is alpha helix, beta sheet, and random coil. That is the data we got from other experiments, not from the direct optical spectroscopy. And what are the conditions they have used? So for this data, which is shown random coil, the condition was pH 6, temperature 25 degrees centigrade. And then they changed the pH to 10.8. And this find that it is actually forming an alpha helical formation. So you can already see a lot of alpha helix present in this structure, a huge number of alpha helix. So at 25 degrees centigrade, at a very high pH of close to 10.8, all the random coil automatically forming alpha helices. And then when they keep the pH same, but change the temperature to 52 degrees centigrade, most of the alpha helices turn to beta sheet. So that is the change they have got. So in the studying of the structure, it is found that it is not a simple absorbance spectroscopic data cannot give you all the information that is required. So you need to have some other contemporary data to support what is actually happening. Simple absorbance data, although they're showing some changes, some shift in the bands and all those things, but they're not any characteristic change where you can follow it, that whether it is alpha helix or beta sheet or anything else. So in that case, it is found that the CT spectroscopic data is actually the most helpful one. So let me draw the structure, draw this data one more time, the optical spectral data. And let me show you also how the data looks for the system. So this data that I have shown you earlier, that is from the same polylysine at these different conditions. So what it is found that if you have a polylysine and you put that in different temperatures, as you vary the pH and the temperature, what is the thing you are going to get? At pH 6, at 25 degrees centigrade, you find that this is the optical spectra of it. And this is the CD spectra. When you run that at pH 6 at 25 degrees centigrade, you get this black line over here. So it clearly suggests that it is actually nothing but a random coil. And it is full-heartedly support from the CD spectra. No other things are present. That is the inference you cannot draw just from the optical spectra on the left-hand side. Then they changed the pH to 10.8, keeping the temperature same. And what they found that the data is this blue data shown over here, with the characteristic positive peak at 193 and 2 humps in the negative region, 208 and 222 nanometer. So that clearly suggests that now you have an alpha helix formation. And that is also supported by the CD spectra. And over here, you can see the random coil to beta sheet. The only change you are seeing some drop in the absorbance with very minimal shift in the actual peak. So that is not a good conclusive data to support that you have such a change from a random coil to alpha helix. And then when you go to a higher temperature, 52 degrees centigrade, over there, what happens that you find this is the new band coming up, which is shown by this brown colored data. Now, instead of 2 humps at 208 and 222, now you have only 1 hump at 218 nanometer. So that suggests that now you have a beta sheet character. So all this data is supported by the CD spectra. So CD spectra is much straightforward data that you can use to find out exactly what is happening. And you can see there's a huge change happening in the solution-based structure of the system. It is going from alpha helix to beta sheet and random coil. All these huge changes are happening with respect to pH and temperature. And CD spectra can undoubtedly give you the idea like what is actually happening over there. So in this case of polylysine, we are taking this example because it is a clean and clear-cut change. It is going from 100% alpha helix to 100% beta sheet in this region, 100% random coil to 100% alpha helix in this particular region. So it is not a mixture of anything. So it's a clear-cut change. And that is why it is one of the data is always used for an example, which actually shows a clear-cut change in the overall structure. So this is one of the examples we like to follow. And it also emphasizes how important CD spectroscopy can be to understand what is the overall structure of your protein structure. After that, we take another example. Over here, I'm going to again through another spectral and CD spectral data, optical spectral and CD spectral data, and show how the changes are happening over here. So it is actually also for two different, one particular different protein absorbed in two different pHs. So there the pH is given over there, pH 5.9 and pH 12. So you can see whatever the protein is, the protein structure we have, we take that at pH 5.9, you can say it is close to near neutral condition. That means close to pH 7. And then we actually make the solution alkaline and we're going to basic condition. And now we go to pH 12. pH 12 is quite a basic condition. So you can say it is basic condition. Now the question is, if I change this pH, what is the effect is happening on the protein structure? And over there you can see a simple optical spectra comparison. It is showing that yes, there is some changes. You can see some shift over here, some change over here, but it is not a clear-cut change. It is not conclusively saying that this is the change what you are seeing. On the other hand, if you look into the CD spectrum, what the change you are seeing. So now take a look at pH 5.9 data. pH 5.9 data, you can see a negative band over here and a small positive hump around 210. So what that data suggests, that this black colored line, the black trace over here, it is suggesting that at pH 5.9, it is actually remaining as a random coil. So you can see there is no particular bonding in this particular protein at pH 5.9. So it was actually a random coil. And not only that, it is also showing how much of it is actually random coil. You can see it is 100%. There is no hump on the positive side, no hump in the negative side. Over here, no positive hump on this side. So it can clearly says that you are seeing 100% random coil. So in the near neutral condition, this protein is such that it is assuming no particular structure, it is randomly oriented, it is having a random coil. However, as you go to basic condition, you get this particular red color spectrum. And what are you seeing over here? A positive band over here. You can see a hump over here, a hump over here, and another hump over here. And if you combine all those things, what you can say? So this hump over here, it is coming at 208 nanometer. On the other hand, this one is at 222 nanometer. And this one in the middle, it is at 280 nanometer. So altogether, what we can say? So it is not a simple alpha helix or beta sheet, but a mixture of it. Because we have both the humps for alpha helix is here, and also the hump for the beta sheet. So you can say that over here, when we actually put this at pH 12 condition, it is actually showing me a mixture of alpha helix and beta sheet. And then, as we were discussing last time, that we can actually deconvolute that how much of it is actually alpha helix and how much of it is actually beta sheet. We can actually do a calculation and fit that data to find out how much it is alpha helix, how much it is beta sheet. So over here, you can see the alpha helix is a little bit higher in concentration because that is creating the background of it. So probably 60%, 70% is alpha helix and 30% is beta sheet. And in the calculation, you can also include some of the random coil to see if it is participating in the overall structure. You might find a little bit of it. But overall, the CD spectra is clearly saying what is the stark change. It is happening over here. You are going from directly a random coil structure to a very much well-structured alpha helices and beta sheet as you are going to a basic condition. Now the question might come that why we are seeing such a alpha helix and beta sheet in the pH 12, which is not happening in neutral condition. So you can imagine that what happens, what are the changes are going to happen if I go to a basic condition. So there are two important parameters. One is the amide backbone. So there is no particular change is going to happen in the amide backbone with respect to the pH in this particular region, 6 to 12. However, the side chains, the side chain residues might have a huge role to play. And over there, which are the group which actually can be affected in this region, pH 6 to pH 12. So over there, those groups will be affected, which has a protein group or a proton exchanging group that has a pKa in that region. So what are those groups? You can have cysteine over there, which has a pKa around 6.5 to 7. This is the range because it also depends on the overall environment, if it is more hydrophilic or hydrophobic, depending on that. And the cysteine has a thiol chain, which actually can have this particular pKa. You can also have the histidine group, which can have a pKa around 6, the imidazole group. You can have the tyrosine group, which has a phenolic OH group, which can have a pH around 10.8. And you can also have lysines, which has a pKa around 12.5. So if you go to close to 12, that means you have started affecting it. So all these things can come together and play a huge role over there. So now you just take a look into the primary sequence of the protein And then you can actually predict what are the changes might be happening, which is triggering such a change from a totally random coil to an alpha helix. Now imagine a random coil means there is no particular structure. And then in the basic condition, it is getting structure. So it is creating some more interaction. So you can imagine that a tyrosine group, which is actually protonated in the neutral condition, and it will be deprotonated in the basic condition, that might play a role. That once it is deprotonated, it is probably participating in certain kinds of salt bridges, like an ionic bond with another cation, and that is probably helping. The lysine should be positively charged in the neutral condition. Close to 12, it should be neutral. So it is probably breaking down some of the bonding. So that might not be the case, because in the well-structured system, you need more well-structured bond, and a positively charged lysine affects better than the neutral. So probably lysine is probably not the system which is affecting this change. Cysteine can, histidine can, tyrosine can. So by that, slowly looking into one and each of the possibilities, you can even sort it out which of the amino acids are probably playing a huge role into this particular change. So that is how you can use CD spectroscopy to find out what are the changes are happening into the overall structure of the protein and how it is connected to the change in the structure with respect to the different parameters like pH, like temperature, all those things can come into play over here. So that is one of the examples I would like to show you. Then comes the other example. So let me find out the figure first. So we have discussed that we can actually look into the stability of a protein at different temperatures. And if the protein is destabilizing, we can clearly see that with respect to the effect of our with respect to the CD spectroscopy. So that we would like to find it out. So over here, what we're actually trying to look, we are looking into So what we are actually doing, we are taking a protein structure, which is starting from this green line over here, which is shown over here, this green line. It is actually the first spectra we recorded at room temperature. And over here, you can see it is very nicely showing that it has a very clear-cut alpha helical structure at room temperature, 25 degrees centigrade. And then slowly you started increase the temperature. So that we are actually doing it over here. So we started increase the temperature. And what we are actually seeing over here, you can see that data is slowly losing its alpha helical structure and going mostly to a mixture of alpha helix and beta sheet over here. So it is not clear-cut alpha helical humps you can see anymore. What you are actually seeing at the end, let me draw in a red line. What you are seeing over here, it is kind of a mixture of beta sheet and alpha helix. You still have some of the signatures over here and here, which shows that it is not 100% beta sheet, but beta sheet is right now actually the major component of the overall protein structure. So as we increase the temperature, it is going to a mixture of an alpha helix and beta sheet. And again, you can do the calculation with respect to the computational calculations, and you can find out how much is beta sheet, how much is alpha helix. And you can see majority of them is beta sheet now. But the important part, what it is saying, that it is losing its shape. It is going from alpha helix to beta sheet. Now, what I want to have, like, what is the effect of it? What is the changes are happening over here? So how I can do that? So this alpha helical positions, this 208 or 222 nanometer, I can plot what is the actual value. So over there, take a look into the unit. It is given as delta epsilon, which is nothing but delta epsilon. And we have discussed over there that this delta epsilon is connected to the phi value. So phi value means molar phi value, to be honest. It is connected to the delta epsilon value by this. And delta epsilon means difference in the molar extinction coefficient for the right hand and left hand circularly polarized side. So we put that in delta epsilon because with that, if I put that in delta epsilon, I am taking care of the concentration. Because if I do this experiment in different places with respect to different concentration, the actual chi values will be different. Actual electricity values will be different. But if I normalize that with respect to concentration, that means molar electricity, or better to go with the delta epsilon, then it is becoming a parameter which is concentration independent. No matter what the concentration you use at any place of the world or galaxy, say someone is using that in US at 1 millimolar, say someone is using in India at 10 millimolar, you should see the similar amount of change because delta epsilon takes care of the concentration. So if I try to find out what is the change of delta epsilon value at 208 nanometer or delta epsilon value at 222 nanometer, what I am going to get. So you can see it starts from a very negative value because it is 100% alpha helix. So you start from somewhere over here, and then I'm going to measure at different temperatures. So it starts from very, say this is the room temperature, 298 Kelvin, and I got a very negative value. So say here is the 0 value. And now as I increase the temperature, the value slowly goes up and then it normalizes. Because after a while, there is no such change. So whatever the change should happen in the structure of the protein, it is already done. So over there, I am going to get this kind of data with respect to temperature. And this data is showing that at what particular point of time, the molecule or the protein is breaking down. After that, no such change. That means whatever the change supposed to happen, it's already gone. So over there, this is the change what we measure, and this is known as the CD melting curve. Because we assume the protein is a globular structure which actually melts or loses its three-dimensional structure as we increase the temperature. Very similar to melting of an ice. So that is why this term melting comes over here. So it is the melting of the solid arranged structure of the protein to an unstructured condition or a different structure of the condition. And over here, we take when it started and when it finished at the middle point. This middle point, we will say that is the melting temperature or TM. And that will define how stable a protein structure is. And over here in this particular data, that is the real life data that you are seeing. So over there, you can see these black dots are the lines that the data are collected, and the different traces are for different proteins. And we try to find out, as you're changing the temperature, you can see what is the change happening in the delta epsilon. They didn't mention it, but assume it is measured at 2.8 nanometers. So you are looking at a change of an alpha helical signature. And you can see it is staying as it is up till this point, up to 50 degrees, it is fine. And then it started showing a change. For example, this red line, you can see the maxima, half maxima is around here. So this will be the T melting for this red color protein. Whereas if I go to this purple color one, this is actually happening a little bit earlier. So now by looking into this data, what we can say that this red color protein is actually more stable compared to this purple color one. So higher the melting temperature, stable is the protein structure. And that we can do it very easily by using a CD melting curve. What we have to do, first record the CD, find out some signature that you want to follow. At that particular point, you are going to measure what is the absolute value of the delta epsilon or the molar ellipticity, and then measure at the different temperature, plot that value with temperature versus delta epsilon or molar ellipticity, and find out what is the trend. And from there, see where the changes are happening, find out the 50% or the half maximum, that will be your melting temperature. And then if you are comparing different proteins, you just compare the different proteins and find out who has the higher temperature of melting. That will be the most stable. Whoever has the lowest, that is the least stable. And why it is important? Because different protein structure actually plays different role in biology, and their structure controls their reactivity. If a protein loses its structure, it might lose its activity. So now coming back to this overall structure, so that is how a change in the protein structure is happening, and it is very much important because, as I was saying, that some of the protein, for example, we as human beings, we are actually running at a temperature within the range of 25 to 40 degrees centigrade. As if we want to measure the body temperature, it comes out around 37, 38 degrees centigrade. That means our blood is actually probably at the same temperature. That means all the protein which is running through the blood, running on the tissues, is running very well at 37, 30 degrees centigrade. Now, if I put someone in a very high temperature, what will happen? At what point of time we start degrading our protein? At what point of time we'll probably die even? So for example, if someone is getting a heat stroke, what happens actually at that point? So for that, if we want to know actually which protein is probably getting affected much, to find out a solution for heat stroke or find out a condition where human can probably still survive. So we want to know actually which particular temperature the proteins are getting degraded. So I want to know the melting temperature of the most important proteins. For example, for us, probably hemoglobin, myoglobin, all the metalloenzymes, all the tissue proteins, all those things. We want to know what is the melting temperature. And from there, we can figure it out which of the proteins are actually falling out with respect to the increase in temperature. And that would give us an idea which are the things we need to fix if I want to go beyond whatever the evolution has bring us to. So to give you an interesting example, for an example, we generally don't survive more than 50 to 60 degrees centigrade. So for an example, if you put your hand in a boiling water, you will like to get a heat shock and you are going to remove your hand as soon as possible. What is actually happening over there? Obviously, heat signals are going through your neurons. It is showing like, please remove it. If you don't remove it, you are actually going to be a boiled egg at the end. And over there, your protein structure will change. Just take a look into an egg. So if you take a egg before boiling, after boiling, you can see a liquid structure then becomes solid. What is happening there? It is a protein denaturation. It is a melting temperature we are just crossing for the albumin, which is present in the white liquidy part. It is actually getting solidified. It is changing its structure. It is melting. It is losing the overall structure. Now, that is going to happen to us also if we actually put ourselves in boiling water. However, it is believed that the first point of the life during the evolution is actually formed very close to boiling water, where the water is getting connected very closely to a lava holes. So in the beginning of the world, our world is much more inhabitable condition than what we are seeing right now. At that time, world was very young, and we have at different positions in the world, the lavas are coming out and getting connected to the atmosphere. By atmosphere, I mean the aqueous atmosphere and also with the aerial atmosphere. We still see some of these volcanoes where it is actually emitting the lavas, and you can see what are the changes are happening. And those extreme conditions are actually believed to one of the parts where the first hints of the biomolecules are probably formed. One of the first nucleic acid, one of the first amino acids probably formed over there, because that is actually enough energy to form carbon, nitrogen, carbon bonds coming out of carbon dioxide, nitrogen, and all those things. And one of those places which is believed to thrive or support the life is actually volcanoes, which is sitting under the sea. So there are also volcanoes under the sea. We don't see it from outside, but it is also living lava all the time. And over here, there, we have this hypothesis that that can be a hotbed for life, because we still find different kind of life forms that is surviving over there, very near to that, where the lava is meeting that seawater. The water is close to 100 degrees centigrade, it's boiling, because it is almost 500 degrees centigrade or even 1000 degrees centigrade. Lava is getting connected to the water. The water is boiling over there. And still we found that there are some life forms is actually surviving there. Now the question is, if there is a life form, they should have protein structure, and how their protein structure is surviving. And then people look into their protein structure, and they found, very interestingly, they have a very subtle change in their protein structure. And by those subtle changes, they actually stabilize their overall protein structure even at high temperature. And over there, they found their metalloenzymes are working even at 100 degrees centigrade, because the melting temperature of their protein is beyond 100 degrees, whereas most of our proteins in the other parts of the world is melting within 70 degrees centigrade. So CD spectroscopy was a huge player in that particular way to find out, is it really the protein structure is playing a role? And when they did the CD spectroscopy at this temperature, they found, yes, the melting temperature measured from the CD spectroscopy is showing a huge difference when it goes to this particularly different biological system surviving underwater volcanoes and the other part of the life. So you can take a look into all these different life forms and find out what are the differences they have in their protein structure that actually allows them, or I should say adapt them, to survive all these very hazardous and extreme conditions. So take a look into it. So that is one of the examples I wanted to give it to you.